This is a guided reading for AP Physics, Chapter 5. This guided reading will allow you to actually skip over some sections if you understand what I say. However, you should still do all the check your understanding questions throughout the chapter, and I'll be highlighting some of the sample problems, and you may want to look at other ones throughout the chapter. So go ahead and open up your books to page 125. And Chapter 5, Section 1 is about uniform circular motion. All you need to know here is that uniform circular motion means it moves in a circle of a fixed radius at a constant speed. Okay? The velocity is always changing because the direction's changing because it's moving around in a circle, but the speed remains the same. You'll see equation 5.1 is a little bit different than we've seen before. Okay, we may have used this in physics, but you had to figure it out in the course of a problem. This is something you will be using in AP Physics, and that is that velocity will equal 2 pi r over t. Okay, 2 pi r represents the circumference of the circle. T is the period. Period is the time it takes to do one revolution or to complete one cycle. So if you take the distance you go in one complete revolution, which is 2 pi r, divided by the time it takes, you've got there a distance over time. So you're representing their speed, and if you throw in the direction at any point while it's moving around a circle, you could also get velocity. So that is an equation for speed when it's moving around a circle, 2 pi r over t, where t is period. Take a look at example problem 1 just so that you get the whole idea of revolutions per minute. You could also do that per second or whatever. So just take a look at example problem 1, then come on back. All right, welcome back. Section 5.2 is all about centripetal acceleration. When something moves in a circle, there is an acceleration because there's a change in velocity. That acceleration points in towards the center of the circle, always in. Okay. As a result, if there's an acceleration pointing in, there's also a net force pointing in along the radius. In physics, that was only ever one thing. In AP Physics, that will often be multiple things you'll have to sum up. More on that later. For right now, I'd like you to look at equation 5.2 on page 127 there in the gray box. And there you'll see the basic equation for centripetal acceleration. It equals v squared over r. If you're concerned about the derivation, most of you, if not all of you, I think can follow the math that's involved. If you're familiar a little bit with limits, you can read some of the other stuff in that section. There's one other thing I wanted to point out. And that is that the direction part, let's use the picture figure 5.4 on the bottom left of page 126. That's figure 5.4, bottom left of page 126. The direction when something's swinging around a circle goes off at a tangent line. So you'll see there at point O, there's a red arrow with a V by it. That shows you the velocity. It's as if I'm swinging Mario ball around my head. If I cut the string, which way does he go? He goes off at a tangent line. So that's how you get the direction part of the velocity. The speed part comes from the previous equations that we've discussed. All right. Turn to page 129. The equation for centripetal force is mass times, shocker, centripetal acceleration. So if you substitute in the v squared over r, you get the equation you see on page 129, equation 5.3, that centripetal force equals mv squared over r. Don't be misled. The left side of that equation, the centripetal force, is really a net force. It's a summation of forces along the radius. There will be, many times, more than one thing added up, okay, on the left side of that equation, or in some cases added and subtracted. Go ahead and if you remember that, you don't need to read that section until you get to, you should look at example problem 7 and do check your understanding 2. But go ahead now and go to page 132, banked curves. This is a section you do need to read. Look at the picture, do your best to understand, and look at the sample problems. Same thing goes for section 5.5. That'll be a good refresher on satellites in orbit. And look at this example problems for both of those sections. So 5.4 and 5.5 you need to read. Parts of 5.5 will also get into the application of GPS. The parts on the GPS are not on the test per se, but they are interesting and they show you an application of some of these equations. Also, don't skip any of the example problems. All right, now take a look at section, if you've done that, pause and then come back. If you've done that, take a look at 5.6. 5.6 has to do with apparent weightlessness and artificial gravity. You should look at the artificial gravity example problem, but I want to talk about apparent weight. We've mentioned in class about the force of the scale up and the force of the weight down. Well, if both the scale and the elevator in our elevator problems and the person are all in free fall, they're all falling downward, okay, towards Earth at 9.8 meters per second squared. There isn't any force of the scale. The force of the scale up will become 0. Look at the picture on the bottom right of page 136. And hopefully you remember this from physics. But as that satellite falls, you see it carves out a parabola there, the circular orbit thing. If you look at half of it, it's carving out, a parabola. So it is, arcing downward. But what happens is it's high enough up that the Earth also curves away. So the ground is effectively not flat. It curves away. As the ground curves away, the object falls, so it just keeps falling. If you remember that from physics, great. If you don't, okay, this picture is a little bit lacking, from my opinion. If you want me to review that, just ask me before, after school, or during homeroom, and I'll give you a quick 5 minutes, and you can get that squared away on why things in orbit have an apparent weight of 0. The acceleration due to gravity in orbit is somewhere between 8 and like 9 point something meters per second squared. It is nowhere near 0 for things that are orbiting. There's definitely a force of the weight down. There's definitely acceleration due to gravity down. Okay, since there's no air resistance, though, they're effectively in free fall. All right, look at the example problems in there for some applications, and then go to section 5.7 on page 138. Okay, this section's got the little asterisks, meaning usually that they're optional or difficult. However, this is definitely relevant for the AP Physics test. This is something that is completely new, this idea of going around in a loop-de-loop like this. And there are more than one force. There's more than one force along the radius in all of these examples. Okay. So first, before you read this, take a look at the bottom right on page 138, figure B and figure A. On figure B, you'll see that at point 4, okay, if something's moving around in a circle, there's one force along the radius. At point 1, there's 2 that are along the radius. At point 2, there's one force along the radius, and at point 3, there's 2 forces along the radius. So, in the corresponding equations that are in this section, you'll see those added up along the radius and then set equal to mv squared over r. Make sure you read 5.7 carefully. That will pop up again and again and again. In 5.8, after you're done reading 5.7, it's just some additional sample problems. Look at those as you see fit. If you need some additional practice, go ahead and take a look at them. That's it for this guided reading. One quick correction. You didn't need limits to understand that one section on one of the equations. Thank you.